3-28 or 3.28. All right, waterfall. It's Niagara Falls, right? All right, so what we have here is water moving along at some velocity. We said that velocity is 2.7 meters per second. And then at some point, it becomes a waterfall, and it falls off like this. So if we model water as some molecule of water, as an ideal particle, then it is a projectile with what kind of problem does it become? It's a half parabola problem, all right? So here it has an initial horizontal velocity, 2.7 meters per second. Right? This is Niagara Falls, so here's Canada over here, and us, Merca over here. All right. So we got water falling off, and as it comes down here, it's going to have some velocity. Remember, it's going to retain the x component of its velocity the whole way down, right? It still keeps moving 2.7 meters per second, right? But then what happens to its y velocity? Its y velocity increases, okay? So now if we have the y velocity increasing, the x velocity staying the same, we have some velocity here that's equal to the vector sum of the x and y components. Okay? Does that make sense? We'll do more of this later, but I just want to prepare you for this kind of thing with the problem we're doing now. All right? The velocity here, this green velocity, is tangent to its path at that instant. It has a y component of we don't know. We'll call it Vy. And it has an x component of V naught, which is equal to the 2.7 meters per second we had before. Now we have a triangle where we have an angle here of 75 degrees, right? Measure 75 degrees from the horizontal. So now, if we take all three of these things here, we can come up with a triangle, right? We've got dubita, 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 dubita. Now that is not a very good example of a right triangle, but we will pretend that it is a right triangle. This is how we can make it a right triangle. Doesn't matter what it looks like. We got that little thing in there. It means it's a right triangle, right? That's a terrible right triangle. All right, here's theta. That's 75 degrees. Now, we have an x component, and we have a y component. So what we have is, why do we care about the lengths of those vectors? Because the lengths are proportional to the magnitudes of those vectors, right? So if we know the relationship among the lengths of the legs of this triangle, we know the relationship among the magnitudes of the x and y components of the velocity at this instant, that it makes a 75-degree angle. Is everybody okay with that? All right, so now, taking this off of here, we know that this is Vy. We don't know what it is. That's what we're going to solve for, because if we know how fast it's going, we know what its acceleration was, and we know what its initial velocity was, we can solve for the distance using which equation? Think about it. We're going to have acceleration. We're going to have V naught is equal to 0. We're going to have some expression for V, and we're going to solve for distance. So what equation? That's the eternal equation, okay? So we'll come back to that in a minute. All right, so we have Vy, and we have Vx here, and we have some angle. So what do we have? Angle, opposite, adjacent. So what are we going to be dealing with here? Opposite and adjacent. Tangent, okay. So we got tan theta is equal to, opposite is Vy, over adjacent, Vx. And Vx is just V naught, right? Because it's a half parabola, V naught is Vx. They're the same. So now what is it we're trying to solve for? Trying to solve for Vy. So now we know that Vy is equal to V naught, or Vx, Vx tan theta. Everybody okay with that? Now, this is what we have right here, Vy, right? This is V naught y over here. So this is what we'll use for this right here. We know this is equal to 0. We know this is equal to negative g. Let's just take downward to be positive. So we'll take positive g, and then we can make this a positive number and this a positive number. We'll just make everything positive instead of cancel out all the negatives. All right? So now we know that Vy, what's our eternal equation? And it's just regular general form. Vy squared is equal to V naught y squared plus 2a delta y to ay, right? We're leaving it positive. Usually we make this negative. Does that confuse anybody? Okay. It's good for you to be flexible if you can. All right, and what is it we're trying to solve for? Read the question, look at it real quick, and I'll wait for you. We'll pause while you think about what it is we're solving for. All right, we're solving for the vertical distance below the edge that it falls, so that is, in fact, delta y. Here's our delta y. All right, so rearranging, we get delta y is equal to, wait, let's talk about our gift first. Right there, v naught y was equal to 0, wasn't it? All right, so what are you going to get? Delta y is equal to vy squared over 2a, right? But what is vy squared? What did we decide vy was? Looking back here, vx tan theta, right? So we get vx tan theta squared over 2g. This is 8y. All right? Do we have all those numbers? Were we given vx? Vx and v naught were the same, right? All right, we know what theta is, so we know what the tangent is. We know what g is, so we can just plug stuff in. Should we do a little dimensional analysis here? Of course we should. Vx is a velocity, meters per second. Square that, we get meters squared per second squared. Divided by meters per second squared gives us meters. Good shape. Delta y is equal to Vx, which was 2.7 meters per second times tan 75, quantity squared, divided by 2g. You guys got your calculators out already, right? All right, so that means that delta y is equal to 5.18 meters. Can you check me on that? I'm trying to remember if that's what it was.
Yeah.
Good? All right. Does that seem like that's far enough? I don't know, it's 15, 16 feet. Probably. Something falls 15 or 16 feet. It's going to be going considerably more than 2.7 meters per second, which is what we need, right? If we're going to have 75-degree angle, this needs to be considerably bigger, this y component, than this x component, so we have a big angle in here, right? Does that make sense? 5.18 meters.